Hello, ladies and gentlemen. How are y'all doing? So today we will be working on chapter 4.8, and the question that we'll be working on is 44. It has three parts, not too long. So we're given a pair of parametric equation, and for the x, it is defined as x equals t cubed minus 3t, and for the y, it is y equals t squared minus 2t. And so, for part A, we're asked, does the particle ever come to a stop? If so, when and where? So let's go ahead and differentiate dx and dy. So we will know the rate of change at that moment that we will be looking for. And so dx dt will be equals to 3t squared minus 3, oops, sorry. And dy over dt, we will get 2t minus 2. So it's just a power down, simple differentiation right there. So if we have to have a particle coming to a stop, um, the rate of change of its motion should be equal to 0 in order to fulfill this. And so dx dt will be equal to 0, and let's go ahead and find when t will be equal, when um, the rate of change of the x and y direction will be equal to 0. And so let's factorize this. So we will get 3 times parentheses t squared minus 1 equal to 0. And by the identity a squared minus b squared equals to a plus b and a minus b. And so with that, we can simplify this. And if we divide both sides by 3, the 3 will go away, and we will left with t equals 1 or negative 1. And so for the y direction, when t will be equal to 0, let's go ahead and find that. So 2t will be equal to 2, just add 2 to the other side, and t will be equal to 1. And so what we have in common here is that both in both the x and y direction will be equal to 0 when time is equal to 1. So this is a recurring pattern that we see for both directions. And so since we have answered the question when, let's answer where. Well, we have the particle coming to a stop. And so in order to do that, we have to plug in our t value. So dx dt, when t equals to 1, we will get so let's go ahead and substitute t equals to 1 back to our original equation, so we can get the coordinates of when the particle where the particle will be at time equals to 1. And so for the x direction, we have t as 1, so it's 1 cubed minus 3 times 1. So it's 1 minus 3, so it's negative 2 for the x coordinate. And for the y coordinate, we get 1 squared minus 2 times 1. So it is 1 minus 2, so it's negative 1. So the coordinate we achieved is negative 2, negative 1. And so let's answer the question. The particle will come to a stop when time is equals to 1 at -2, -1. So that is the position and the time that the particle will come to a stop. Alright, let's move on. So for part B, we are asked, is the particle ever moving straight up or straight down? If so, where and when? And so in order for a particle to move just straight up or down, we have to have dx over dt equals to 0, but dy over dt not equals to 0. So we don't have to differentiate it again because we already have what we have right here. So let's copy and paste what we achieve right here, just to save a little bit of time. And so let's analyze again the answer that we got. So we have to fulfill the requirement of dx dt being equals to 0, but dy dt not being equal to 0. So the only time that can fulfill this requirement is when t is equals to -1, because dy dt would not be equals to 0 at time equals to 1. So since we have answered the question when, let's answer where. So same thing we did just now. Let's plug in negative time equals to -1 into our very, very original parametric equations. And so let's go ahead and substitute t equals -1 into our equations. So we get -1 cubed minus 3t, and we will get -1 minus, 3 times -1, excuse me for that. So we got -1 plus 3, so we'll end up with 2. And on the y direction, we will get -1 squared minus 2 times -1. And so we will get 1 plus 2, which is 3. So let's draw a conclusion here. So the particle will be moving straight up or down at time equals -1 at 2, 3, which is this coordinate. Alright, last part of the question. So we're asked, is the particle ever moving straight horizontally right or left? If so, where and when? Alright, so it is just the vice versa version of this theory right here. And so in order for a particle to be moving parallel to the x-axis, dx dt will be equal to 0, but sorry for that. So dy dt has to be equal to 0, but dx dt not. And so, just like what we did, let's copy and paste this whole chunk. Oops. Let's copy and paste this whole chunk to the bottom to save us some time. Oh my god. Oop. Got it. Alright, so let's analyze the results again. So, on the x direction, the rate of change is equal to 0 when time is equals to 1 or -1. And on the y direction, it is t equals to 1. So from what we can see, none of the time can fulfill our requirement being time being dy dt equals 0, but not for the x direction. And so we can draw the conclusion that since there isn't a place where dy over dt equals 0, but dx dt is not equal to 0. So therefore, nope, there isn't a place where or when the particle is moving straightly horizontal. So I hope you guys understand what I was explaining, and have a great day. Thanks.